Confidence intervals. Well, what is a confidence interval? Within the yellow box fits pretty good. I mean, it represents the range of scores that are likely if a survey or experiment or study were to be repeated. So if you want to be really confident, make this range even bigger. So in other words, I want to be 98% confident that if I repeat this, I'll get this answer in this range. Well, that range has got to be huge, right? If you want to be only 50% confident, then that range doesn't need to be so big. So how do you calculate these ranges, these confidence intervals? That's one thing that we're going to talk about today. I guess it's going to start right off with that. Confidence intervals. So we have an equation for it. Let's see. So it looks like we have a plus or minus. So right away we're going to have a range, right? Our x bar will be in the middle, and then we'll have some range, right? The plus part and the minus part. So we'll have a range. What's x bar again? Jackie, what's x bar again? What's x bar again? The average. Is it your average, or is it the... Remember, because we had two averages last time. We had this big distribution of all possible results, and then we had its average. And then we had the average of your little experiment. Which was which? X bar was... Does anyone remember? X bar was... It was your sample average, your average from doing the lab. So like do it 5 times, you calculate an average. That's an x bar. So this is that's your value. What is mu? Melissa, what's that symbol mu? What's this? That's the population. That's the true answer. You take the average of all possible measurements. This is theoretical. And then you get the true answer, the population mean, just like what Melissa said. Population mean or average. Bless you. Okay. So if you want your average that you're going to calculate in your experiment to be right, within some range, right? We can calculate it using this, and that's what's behind this little box, or in the book. Okay. TS over the square root of n. So if you want to be 98% confident that your average is within the right range, it's got to be a big answer. Right? And how this range gets bigger and bigger and bigger with higher and higher confidence is what parameter is going to be changing in this plus or minus thing. Andy, what part's going to be changing?
Standard deviation.
Well, no, because you did your experiment, right? And you calculate a standard deviation, so that's not going to change on you. What changes to make this confidence interval bigger and bigger and bigger? It's not S, that's standard deviation. It's not N, because N is the number of times you did the experiment. That can't change. You just want a bigger confidence interval. It's the T. It's the little T number, right? So S is that equation for standard deviation. No, you should really know how to do that in your calculator. And then you have to figure out the equation, right? That's an ugly calculation. N is the number of measurements. T is right from this T table. So if you want a bigger and bigger, a wider range, more confidence, you just have to use a bigger T. And that's what works here. If you look at their confidences, right? 99.9% confident. Look how big some of these T numbers are. They're huge. If you want to only be 50% confident, look how tiny those T numbers are. Very narrow range. Okay? So That's the game they're playing. But how do you pick a t number, right? Because it would be nice if this little n was right here. Oh, just erase this degrees of freedom and write little n. We can't do that. What's degrees of freedom? It's kind of complicated. That's what all this is about. I moved this down from what you have. But you really got to know it. There's nothing stopping them, actually, from having a table with n instead of degrees of freedom. But this is just their conventional way of doing it, so we have to understand it to read the table correctly. So follow this. In general, the degree of freedom of an estimate, so this is an estimate, right? We're trying to make an estimate here. The degree of freedom of an estimate is the number of independent scores that go into the estimate minus the number of parameters used as intermediate steps in the estimation of the parameter itself. Now, if you read that really slowly and carefully, it might make a little bit of sense to you. But I think in layman's terms, what is a degree of freedom? It's a mathematical restriction that is put in place when we calculate an estimate of one statistic from an estimate of another. So, for example, standard deviation, to use the technical jargon, it loses 1 degree of freedom. There's all these parameters, and we're losing one because we used an estimate to calculate this estimate of standard deviation. What statistic or what estimate is always used to calculate standard deviation? What's the equation for standard deviation? What statistic is it using?
The average?
It's using the average, right? Somebody remembers, right? The standard deviation, I don't know if you remember this, is the square root of the sum of what?
Of your x value minus the average value.
Your measurement minus the average divide by
The number of times.
close n minus 1, right? Is it squared in the numerator? I forget. X minus x bar. Is it the square of the differences? I think it is.
What is it?
I think that's squared, if I remember right. Okay. But I don't think you need to know this equation. The point is x bar is in it. So, and standard deviation itself recognizes that. You're not dividing by the number of measurements, you're dividing by the number of measurements minus 1. So it's losing a degree of freedom. So I guess the point of the story here is that when you want to get a confidence interval, you recognize it has standard deviation in it. So when you look up a t-value, you can't look at the number of measurements. You have to look at the number of degrees of freedom. And you sucked one up because you're using standard deviation. And it has n minus 1 degrees of freedom. So if you have 6 measurements, you can't come down here and use 6 degrees of freedom. You only have 5. So I think when you're using this table, just realize that's n minus 1. It's the same as what's in the denominator of the standard deviation expression, if that helps you remember. But the degrees of freedom in using that t-table is always the number of measurements minus 1, because you've lost a degree of freedom. Okay. So we can calculate these confidence intervals. And I'm sure there's some homework on that. Okay. T-tests. So confidence interval was when, okay, let's calculate a range of numbers, and we're 80% confident that if Marlena does this, that she'll get an answer within this range. That's what confidence interval is all about. Or she wants to report it and say, this is my confidence interval. that I did this experiment and here's my confidence interval that if you repeat it, I'm about 98% sure you should get an answer within this range. Is that the same as uncertainty? Is that the same as uncertainty? Experimental error. Is it the same? What do we usually use as experimental error? If she did this experiment a whole bunch of times, she could calculate the confidence interval using that equation, right? She could. It looks like there's this nice plus or minus thing there, so it doesn't look like a nice little uncertainty. And I guess you could, but it's not meant to be an uncertainty. There's more information that's saying you're 98% confident you're going to get an answer within that range. So it's really bigger than an uncertainty. Usually in uncertainty, all you're using is what? Aren't you just using that? You do something a whole bunch of times, you calculate a standard deviation, and then usually report your answer as, oh, this has 12 weight% calcium in it, plus or minus 2%. And then what is that 2%? That's just your standard deviation. You did this 60 times and you calculate standard deviation of those 60 results. So traditionally, that's all uncertainty is, just standard deviation. So confidence interval, I don't think, is an uncertainty. It's bigger than that. It's a wider range. It has more meaning. T-tests. Now, what's the point of a t-test? Let's see if Ida can tell us here. T-tests are used to compare blank of two sets of data. Averages. Very good. Okay, so the book discusses 3 cases for using t-tests. So you are comparing averages of 2 sets of data. So they're coming up with 3 possible scenarios here. But the point is, whenever you do t-calcs, you're going to calculate a t. And whenever it's bigger than the t in the table, then the difference is, Kelly, is significant. Yeah. At the percent confidence level that you pick in the t-table, right? T-table. Exact same t-table that we use to calculate confidence intervals, t-values. Okay, they have, okay. Here's the first case. Replicate measurements and the true value is known. So you do something over and over and over again, get an average, and the true value is known. Here's an example. This little bottle. That little bottle ran like, I paid, I think it was $600 and blah blah dollars. Just call it $1,717. And what it is it contains soil from a super site. That's, in other words, those, you know, those sites in where the EPA says, oh, Superfund site, where, oh, it's so bad that you can't do anything with this area. And somebody's making some money off of it because this material, that soil at this Superfund site where this came from, has been analyzed a gazillion times. And they are pretty dang confident they have a true answer for the amount of mercury in that bottle. So when I have someone do a mercury research project, they have to analyze this first. Only I know what the answer is, right? So then we can do a t-test here of case 1 and see if they can move on and actually analyze compounds and out there in the real world, right? Like, did you hear out by Nacogdoches? There's a cement factory out there, and I had a class with a teacher, and she said that, I don't know how we got to talking about this, but she said that some mornings she has to go outside and just wipe off her windshield and all that. It's dust coming from the cement factory, and she was kind of worried about it. So that set off some ideas, and we started just plotting, finding out the mercury that's around this cement plant out on Nacogdoches. So we spent a summer on that, and it was interesting. And then towards the end of the summer, 'cause you're just walking along this really high fence line, right? And you're just taking soil samples the whole way around. And towards the end, where we reached this part where the grass was was bending outwards, right? So something overflowed, right, and went over there. So when we took samples from that spot where the big grass was bending outward away from the fence line, then we had 200 parts per million mercury, which isn't, EPA isn't going to come in and force them to dig up the soil. That's around 1,000 parts per million mercury. But it's getting there, right? I wouldn't want to be messing with that stuff. So the point is it was kind of interesting. I don't know how I got to. Anyway, if you're going to do this, or if that student did that, they had to look up a T-table number. What do they use for their degrees of freedom? What would you guess? You see an S in here. So probably just N.
Why would it be -1?
N minus 1. Because it's the same. Because you're using standard deviation. You're using essentially standard deviation. Standard deviation has N minus 1 degrees of freedom. So therefore you use N minus 1 degrees of freedom.
I guess what I was asking was, I think with the standard deviation, with the population, it's all the stuff that you said before over N, whereas with a bunch of averages or something, it's over N minus 1.
No.
I think they're different.
Standard deviation, this is how you calculate standard deviation. And they're saying that you're using the statistic average to get standard deviation. So you lose a degree of freedom. So if you have 20 measurements, you essentially have 20 degrees of freedom, as long as you're not calculating anything. But once you calculate standard deviation, it's a statistic that's using another statistic. So there you're losing a degree of freedom. So this T number is just like calculating a standard deviation. So you're losing a degree of freedom. So we should be, again, realizing when we use this table, it's N minus 1.
I was treating it as a population, but just because you take a trillion samples doesn't mean it's a population.
Oh, we're never going to hit the population.
Yeah, it's still the number of samples.
Yeah, we are never dealing with mu or sigma, because that's for the population. We don't know those answers. Except here we're kind of pretending that we do, because I spent $617.
Yeah.
So I'm saying that I do know the true answer. I'm saying that I do know the true answer. N would be what? Danielle, what would N be? Number of measurements, yeah. S, standard deviation of all your measurements, the average. Okay. What do these bars mean? Absolute value. Yeah, good. Okay, the second case. Replicate measurements are done, but by two different people or groups. Okay? So Desiree and Jackie. When the standard deviations are similar, we use equations 4.8 and 4.9. So I guess we calculate their two standard deviations, and then we want to compare. Again, we want to compare and see if T-calc is bigger than T-table, to see if their two averages agree or not. And look, this stuff is starting to get ugly, isn't it? You have to calculate an S pooled, and look at the equation for S pooled. But just remember what everything is, right? They have little, how about the N1 and the N2? Or X bar 1 and X bar, what do these 1s and 2s stand for, Andy? What would you guess? You're two different groups or people, right? You could erase the little 1 and write Jackie. Erase the little 2s and write Desiree, right? So it's just the two groups. It's likewise with N1 and N2. N would be the number of times that Jackie did the experiment. N2 the number that Desiree did the experiment. One thing that I thought was kind of interesting was when the standard deviations are similar, use these two. Well, what qualifies as similar? Right? This is statistics. You can't just say, oh, that's close, right? You have to do the F test. Might as well just talk about it now. The F test. When F calc is bigger than F table, then the standard deviations are probably, just like before, T calc bigger than T table. F calc bigger than F table would mean different, right? It means negative things. With, I got to read that small print. See, this table is only at 1%. 95%. It only has one kind of percent listed, so everything's at 95%. So this is what you'd have to do the F test first to see if they're similar or different. Well, if they're similar, right, do the F test. Oh, great! I can just use 4.8 and 4.9. But if they're different, according to the F test, then you use 4.8a and 4.9a. You just look. It gets that far. You're gonna have to start looking in the book. These equations are getting ugly. Okay. Oh, you want to compare T calc and T table. Now you've got, look at this. You're using two standard deviations. You don't just have N1 measurements, you have N1 and N2 measurements. So your degrees of freedom, oh, here I wrote it right here. Here's your degrees of freedom. All right? Your number of measurements, so N1 plus N2, and then minus 2 because you lost 2 degrees of freedom, one from each standard deviation. Okay. So that's pretty much the only time. I think that's going to be the only time when you're subtracting 2. Otherwise, it's always n minus 1. So the only time that you're going to be subtracting 2 to get degrees of freedom is when you have this 2 different people or a group thing going on. Then you got to realize, oh, my degrees of freedom is going to be the total number of measurements, but minus 2 because I have 2 different people, 2 different standard deviations that I'm worried about that I have to use in the calculation. And then there's case 3 for replicate measurements but done by 2 or different groups of people. Averages from 2 different methods. So not 2 different people anymore, 2 different methods. Heck, I don't even have the equations written here. So we look up in the book, it'd be equations 4-10 and 4-11. Okay, so they must really be getting grotesque. They must be getting so grotesque that I think they're getting so long that you're not going to see it on a quiz or anything. It's just something to be aware of. But the rest of it I think you could see. Q-test. Maybe you've heard of the Q-test before. Man, this is the way to make a nice table. Degrees of freedom aren't even here. They just have number of measurements, which kind of makes sense because they're not using standard deviation. So degree of freedom really doesn't make sense. They could have listed degree of freedom, but it's the same as the number of measurements. With the Q-test, when Q calc is bigger than 2 table, you do the Q-test for this questionable data thing, right? You're doing your titrations in analytical lab, and it's just, oh man, each one's taking like 20 minutes. Smith says I got to do this 4 times, and Andy spills a little bit on the last one, right? He's supposed to get the same result all 4 times, but he knows he spilled a little bit. But man, I don't want to lose any points for only doing this 3 times, so he does a Q-test, and to see if he should throw out this questionable result or not, or maybe it's just you have well, whatever reason, maybe he didn't spill anything, it's just questionable. So when Q calc is bigger than Q table, then the questionable data should be removed. So yeah, it's all, I wrote them all this way so that this with 90% confidence. If you use that table, you'd be 90% confident. Okay. So to do this whole Q-test thing, you have to calculate gap over range. So you've got a whole bunch of data, and you're supposed to calculate gap over range. Well, Kimberly, let me give you a whole bunch of data here. You have 78, 77, 82, and 76. How would you do this whole gap over range thing? Okay, did you hear? She said the range, for example, would be like 76 to 82. So what she's doing, what I do on this first is I list them from lowest to highest. Right? List them from lowest to highest. Otherwise, you might screw up somewhere. 76, 77, 78, and 82. Okay? And then, so that's what I would do first. The range is always going to be the highest minus the lowest, right? It'll always be that one minus that one. That'll always be the range. What's the gap?
Is the gap the average of the numbers closest to each other?
Not average, though. It's just, like, for example, we list them from lowest to highest. Which number are we going to be doing the Q test on?
Oh, 78. Oh, sorry. 82.
Probably 82. But there's nothing stopping you from doing it on 76 also. It's always going to be the outliers, right? That's where your Q test is always going to be. But it seems like 82 is more of an outlier than 76. But you should really do them both. But you do 82. Okay? So my gap would be what? This difference between those two. 82 minus 78. So it's your outlier and its nearest neighbor there. That's your gap. Divide that by the range, get QCalc, find a Q table, compare the two. And if QCalc is bigger, toss out 78. And then try the Q test again until things finally start agreeing for you. F test. Oh, that's problems now. Alrighty then. Let's see. The percentage of an additive in gasoline was measured 6 times with the following results. Find the 90 and 99% confidence interval for the percentage additive. How do you do that? Jeff, how do you do that? It says find the average, find the standard deviation. Whoa. Where is it? All right. Really, my answer is this part right here. He's right. You're going to have to find the average for sure. You're going to have to find the standard deviation for sure. You're going to have to look up a T number from the T table, right? And you also need to know the number of measurements. So there's your answer right there, because that's your interval. What did I say? X bar plus or minus TS over the square root of N. Oh, this is a good one. You got to see if you can do that in your calculator. Because if you don't know how to get standard deviation in your calculator, you're going to have to know that equation for standard deviation. Okay? So I can show you how to do it in Jackie's calculator. But if you have one of those big honking TIs, you better ask Sabina. You know how to do it? She does. So if you have a big TI, ask Sabina. If you have one of these, I'll show you. Okay? So let's start with this one. So if you got the solar one, what I'm going to do is I want to, in X bar equals S equals. I'm just going to plug them all in the calculator, and you should too if you have the big TI. plug them all in the calculator, and that's all you do. You write x bar and s. Okay? So, first thing we have to do in this one is get it into standard deviation mode or statistics mode. So, I like to call it standard deviation mode because if you see the little under mode, there's a blue one, little blue highlight. It has a dot with an SD. So SD is for standard deviation. So, but it's mode. And in front of the standard deviation is a little dot. So push the mode button and then the dot button. Right? Push the mode button, little dot button. You notice that the SD popped up in the corner? So for you to continue, you got to have that SD up there in the corner. Okay, so now we're great. Now let's make sure all of our statistics is cleared out, the little memory. So see above the AC is an SAC. That's statistics all clear. And it's yellow, so you have to push shift first. So I'm going to push shift and then statistics all clear. I'm sure it was cleared anyway, but this way it's guaranteed. Okay, so we're cleared. Now what I'm going to do is I'm going to enter every single number, and after every time I enter a number, I'm going to push the M plus. That's my little data button. So I'm going to push 0.13 M plus, 0.12 M plus, 0.16 M plus, 0.17 M plus, 0.2 M plus, and 0.11 M plus. So did you get them all in there? Okay, now you got to hunt for this little button. We're looking for X bar. It's above the 7. And X bar is yellow. So that means you have to push shift and then push the 7. And there's our average, 0.148. Okay? Now see if you can find the standard deviation button. It's right above what number? Do you see it? Above the 6 is the N. That's the number of measurements. We could do that one, shift 6. That means there were 6 measurements. Okay, it's either going to be 8 or 9. Do you see it? Above the 8 is a sigma, my eyes are bad, N. And above the 9 is a sigma N minus 1. Okay? Now, do you remember when I wrote the equation for standard deviation? Where did I write it? Oh, there it is. You go sideways. Standard deviation has a N minus 1. If you want to calculate population, it's just an N. But we don't want population. We want standard deviation of our measurements. So it has to be N minus 1. So it would be shift 9. You get like 0.034 or something? You got 0.03, Desiree, you got 0.034? Oh, great. Okay, so you guys using your big TI calculators, you should be getting those results too. Okay, so now we got both of those. Now we can calculate our interval. Oh, we have to look up a t. So we'll have our average. Just get it into this format. So we'll have our average, 0.148 plus or minus. Our S was 0.034. And we had 6 measurements, right? So that'd be the square root of 6. We've got to multiply it by our t. So we have to look up a t. Okay. What percent confidence did they want? Oh, they want 90 and 99. So okay, let's do 90%. And then over here, we'll do 99%. So for the 90% t, which number would you look up? What t number would you look up? Good. 5 degrees of freedom. That's the degrees of freedom you got to look up. And what's the T number? 2.015. You should be using 2.015. All right? When you do the 99%, everything's the same. It's just going to be a bigger T because it's a bigger percent confidence. So it'll still be 0.034 divided by square root of 6. We just have to plug in the right T. So now it's 99. The new T is going to be, anybody see it? It has to be degrees of freedom of 5 again. I see 4.032. Do you see 4.032? Yeah. It should be 4.032. So we've got to calculate our answers there. Now, how do we write these again? We want to follow the same. Do you remember the convention? If I write out all these digits, did you get like 0, 2, 7, whoop, point? Zero point 0.027, 9, 6, 9, right? That's not how we're that's not our convention in writing plus or minus things. What was our convention? Right? How many digits were we supposed to use? How many digits? How many sig figs were supposed to be in here? Our uncertainty kind of story we were talking about it. Even though this isn't an uncertainty, we're supposed to follow the same rules. We only use 1 digit. If you want to use 2, it needs to be a little subscript, right? Remember that? So there's several ways you could write this. You could write it as plus or minus 0.03, or you could write it as plus or minus 0.2 with a little, but it rounds up though, because it was a 9, so it should be a 8. So those are the 2 ways you could write this. You shouldn't write it this way. Right? Or you could write it as plus or minus 0.02 with a little dinky 8. Remember, that's how they like doing this? Okay. Oh, we're out of time. So there's always more problems we can work through, but there's a lot of good examples here. And come by, I'll be glad to help you. And have a good weekend.